This is my drying rack and it has a problem. The plastic joints here start to break. You can see the crack line everywhere. So in this video, I'm going to remove all of this joint, make a 3D scan and reverse it and 3D print. I think I will print with the PTG. The joint need to have the elasticity to be able to withstand large bending moments before it start to break. So there will be one joint, that will be 2. This one is 3, and on the floor here is 4. So there will be 4 type of joints. Okay, here's all the broken joints. So I will pick the one that is not so much in the broken. This one is too much broken. This one is broken. This one look intact. So there are 2 aluminum profiles. This is the bigger one. The bigger one will go over this joint. And this will be the stopper. It's quite fit. The smaller profiles will go inside of the plastic joint. I can try to make the wall thicker. I need to use the same depth for the end of the pocket because they have a pre-drilled hole here. So if the pocket depth is wrong, it will not fit. Okay, let's start with the 3D scanning. I'll use the Sermoon S1 for making this 3D scan. Okay, I will start with the groove marker. Point cloud. I will use 0.2 mm for the resolution. Scanning parallel lines. Okay. Single lines. Okay, so I will fuse all 3 of the scans with a 0.2. Okay, let's talk a little bit about the fusing function in the Creality Scan 4. This function, point cloud confidence, if you lower it, for this example, I will lower it to 30%. It will remove the low quality point cloud, so it will not show after the fusion. Let's try. So now you can see that all the low quality point cloud is removed. So if I use 70%, you will get more capture data, but it will be in a low quality. See here, it's gonna be a lot more point cloud show up, but the quality is lower. Next, I'm going to merge them together, the 3 scan. Let's try to do automatic merging. Yeah, it can do automatic merging because we have 3 scans, and if you do only 2 scans, you need to merge this manually. Okay, one thing that you are going to notice is the quality of the point cloud after merging with multiple scans. In Creality Scan 3, the quality of the point cloud after merging is very good. So what you're gonna do about this, you have to mesh it. 0.4. If I click on apply, after meshing, all the boundary noise will be removed and the result is very clean. The dimension from the mesh and the point cloud will be different. For this object, the difference will be around 38 microns. I have already addressed this issue to the Creality that for most engineering use, the scan data has to be output in the point cloud format, and they have to reinstate the point cloud merging function from the Creality Scan 3. I will fuse the for scan fusion. Okay, now the point cloud is really dirty, but when you mesh it, 1.2 million. But when you mesh it, you get a very nice and clean mesh. It looks very different from the point cloud. All the noise that was captured was removed, so they are forcing the user to use the scan data from the mesh. But you can also convert this back into the point cloud with the cloud compare. Seven lines cannot see bottom of the hole. Do this fourth scan. Okay, I will fuse all 4 scans. Okay, let's merge them together. 1, 2, 3, and 4. Okay, it's all merged. Let's do some matching. Okay, so it looks totally different. And this bottom of the pocket is about 3 times the width. It's go very deep here because the wall is in a white color, so the 3D scanner can see deeper. If it's black color, it's gonna be about 2 times the width. So all the bottom of the pocket is scanned. Let's merge them together. 1, 2, 3, and 4. Okay, it's all there. Okay, next I'm going to export this as an OBJ format, and then I bring it into Cloud Compare. Okay, this is a 3D scan of MX threads on the caster. It has only 0.6 millimeter profile depth, so I cannot print a female thread with this because the nozzle is already 0.4. M8, it has a standard pitch for 1.25 millimeter, and when I measure from the point cloud I get 1.26. Okay, I will show you one sample on joint number 4. So this is a mesh and I need to convert this into point cloud so that I can use it in Autodesk Inventor. So I will click on edit mesh sample point and then I will create a point sampling for 1.3 million points. So it's only take a few seconds to do this. So when I turn off the mesh, I will get a point cloud. Next, I'm going to align this to the XY plane. Click on here, 3-point alignment, 1 point, 2 point, and 3 points. So now it's aligned to the XY plane. And next, I'm going to rotate it along the Z-axis using the edge of my monitor. Use it as a reference. Okay, now it's aligned to the XY axis. Next, I'm going to move it to the origin point. Move bounding box center to origin. Now this part is in the origin point and it's ready to be reversed in Autodesk Inventor. Okay, so here's in the Autodesk Inventor. I combined all the scan data into a single RCP file. So I can choose to turn on and turn off each scan using a navigator command like this. And to create a cross-section profiles, I will do like this. I will crop the point cloud into a very thin layer like this. Create a sketch. This is how I create a symmetry axis. So I can draw just 1/2. I will draw the inner wall because this is the point where the aluminum profile will be insert. So I just trace the point cloud like this. This part is damaged, so you need to understand this. Next, I'm going to offset for the wall 3 millimeters. It's going to be thicker than the original profiles. So that's it. So modeling this part is quite easy because it's aligned in a 90 degrees angle. This is a 3-member joint. So I show you how I made this. First, I copy the sketch from the profile part that I made earlier and then I extrude it to here using the point cloud as a reference. This is a stopper. This small one is a stopper. And then I make a second sketch here on the stopper and then I extrude it. Okay, next I copy the second sketch from the profile parts, make an extrusion. Okay, here's the third profile, make an extrusion. Okay, next I create a hose. I turn the part into the clear transparent color so I can see the position of the hole more clear. And I made a cutout for the Phillips head screw, just 9 millimeter. Create another hole here. Cut out for the screw. Another hole here. This hole is quite damaged, so I need to do an approximation for the location of the hole. And that's it. It's quite easy to model. The modeling doesn't take long. Okay, one thing to notice. When you do a lot of reverse engineering, you will learn from the original designer why they do this and why they do that. Okay, if you look here, this wall has a taper wall. Because it doesn't have a stopper, it's go all the way into that. The reason that they don't put a stopper here because they want this part to be hollow. If it's a solid, it's going to be expensive to make. Unlike the other joint, it's the only joint that has a taper wall. This wall is taper, but I'm not going to make this taper wall. It's very difficult to remove. I will just make a parallel wall instead. And then I can make a small cutout in the wall here to make it stop. Because they cannot do this with the injection mold, but I can do this with the 3D print. Right, the part is not complex. I just need to add thickness to the wall and maintain the position of the mounting hole and the stopper. That's it. Okay, let's send this to the slicer. Okay, so here is the most difficult part of this project, 3D printing, because the part is hollow and this is a 4-member joint. So how are you going to print this with a minimum support? So if I just print it as it is, so it's going to create a lot of support, especially in the inner wall. This is the contact point of the aluminum profiles. You can't have support here. It's going to be difficult to remove, and if you can't remove them all, it's going to obstruct the insertion of aluminum profile. This is not the orientation that I would do. So let's see what else I can align this on. So if I print it flat on this side, let's see what is going to happen. Okay, it's the same. You have a support inside of the pocket, which is not ideal. The best way to print this part is by turning it in 45 degrees along z-axis first, and then I'm going to turn it the second time along the y-axis for 45 degrees. All the tube will be aligned in 45 degrees. So if I slice it, so I can print this with a minimum support, and the support will only be on the outer shell. So in the inner shell there wouldn't be any support. I need to add the support manually, and I need to paint the support in this area all the way down here. Let's slice it. Okay, so when it's print into about this height, it will have support wrapped around it, so it shouldn't fall. And next I need to do a mirror of this part. Because I draw only one side, what I have to do is just click here, clone. So I clone one part here, and I'm going to mirror one of this. You can mirror it along any axis. Mirror is mirror. Once mirror, it's going to be a mirror part. Good thing about the Orca slicer or the Creality slicer, once you mirror it, it also keep the support painting. The support painting also mirror. So for all the joints here, I align them with the 45-degree angles so that the inner wall of the tube will need a support. It's really nice and clean surface. See here. So if I lean the part 45 degrees and put support in, the surface defect from the support will be very minimum. This is final print. Okay, next I'm going to make a wheel assembly. I'm going to put this wheel into this. Okay, this is fitting I made. So it's tight fit. I'm going to thread this in. It's about 0.2 millimeter larger than the thread size. And you can just thread this in because you can't print M8 female thread. The pitch is too small for FDM printer. So I just print a solid hole. And you can tap this in. Just like this. And next I'm going to lock this with a self-tapping screw. Just like that. So it won't be pulling out. So that's it for the wheel assembly. So this is all the part I made in the past 24 hours. Take a long time to print and cost me one roll of the PETG filament, somewhere around 15 US dollar. Guys, how the wheel assembly is locked into the profiles.